For those of you who don't know me, good afternoon. I'm Jun Hao, or some of you may know me as Alex. Okay, I'm a postdoc in Quex Group. So doing research is fun. Okay, we are at the edge of knowledge. We meet many different people. In fact, I like to talk to different people, and I'm sure you have experience as well. I still remember one of the first times that I interacted with other people, talking about my research, and so interacted with people. Yeah, and then they were like, "Oh, hey, Alex, nice to meet you. What do you do for research?" I would say, "Oh, great. My research topic is DFT." And I remember that time, right? The person gave me this reaction. Oh, DFT? I'm surprised that people are still doing things in DFT after a few centuries. Of course, my immediate reaction, what do you mean by a few centuries? DFT is found in 1960s. His reply was like, really? Discrete Fourier transform is found in the 1960s? But since then, I've learned my lesson, okay? Nowadays, when I first talk to people about my research, I would just say, density functional theory. So who here has not heard of DFT before? Density functional theory. There are some people who have not heard about density functional theory before. So nowadays, so when I introduce my research topic, right, there are a few common reactions that I have, right? So first common reaction is sort of like, oh wow, DFT, I heard it before. Is that black box method, right? That we use it to calculate something, but I don't know what it is. In fact, I've met some people who are very proud that they don't know what DFT is. They were just like, oh, DFT, that thing that I don't know. Okay. They are very proud that they don't know. There are also another category of people when I say that, oh, I work in density functional theory. And they were like, oh, wow, that very, very difficult subject, right? I'm not going to touch it. And some may go to the extreme. It's just like, oh, density functional theory, quiet, smile, nod, and just slowly move over. So since then, right? So whenever I talk about my research topic, I was like, okay, I have the preparation, psychological preparation that people are not going to ask me about what my research is about. In fact, when at the handful of times when people ask me, okay, what your research is, actually ask me to elaborate, I'm surprised. So I decided that use this particular time to just focusing on the basics of density functional theory. Now, some of you may ask, why would I want to talk about basics of density functional theory? Well, for me personally, it's because I really like DFT. For me, it's like an amazing field, gives me joy, and I want to spread that joy to you. But the more important reason, more important question is, why should you learn about the basics of DFT? To that, then I would just have to tell you that DFT is actually a very common, often used calculation tool that is used in many different fields, like for example, physics, chemistry, material sciences, and biology, right? You just see it anywhere. If you don't believe me, you can do it right now, whip out your phone, go to Google Scholar, type in DFT, just these three words, and you see how many results you have. To save you time, because you are eating, yeah, I've done it for you, and I've filtered it only just for like since 2024. Now it's only March, right? And immediately you see almost 10,000 results. Just this year, there are 10,000 results just for DFT. So you can see how widely used this method is. On another perspective, like, let me ask you guys, what do you think is the most cited field? You want to guess? Biology, correct. That's perfectly fine. So in 2014, so Nature published this top 100 papers, and among them, there's like the top 10 most cited work. You're right, perfectly right. The most cited paper is the biology field. But the only other field that make it into the top 10 that is not biology is DFT. So wouldn't it be nice for us to know how this one of the most cited field works, right? How DFT actually works. So this is why I'm here today, to try to demystify density functional theory. Okay, to tell you what it is, how it works, and what it can do. It's not something that's so difficult that you can't understand. I hope after this presentation you can understand that the concept is actually not that difficult. So meanwhile, just sit down, relax, eat lunch, and enjoy the show. So let's start with the first question, right? What is density functional theory? So to do that, we have to go back to what we learned in quantum mechanics, right? So in quantum mechanics, we learned that suppose we have a quantum system that we want to study, okay? It can be atoms, it can be molecules, or it can be crystals, whatever you like, okay? The standard approach is what? First, we have a system, we write down the Hamiltonian. From the Hamiltonian, we plug it into Schrodinger equation, and then we get the wave function, right? And from the wave function, we can get whatever properties we like. So that's the standard thing that we learn in quantum mechanics. And often, when we are looking at properties of system, we look at their equilibrium properties, right? So in equilibrium, we know that systems tend to go to ground state, the state in which they have the lowest energy. So often we also look for ground state properties of the system. And also, as you learn in quantum mechanics classes, there are only a handful of systems in which you can solve analytically by pen and paper. Most of the time, you need to use numerical methods. Okay. So now, this is what we learn in quantum mechanics. Now, suppose if I have a system and I only have one particle, okay? Easy. The wave function is just going to be described by the position of that particular particle, right? So imagine simplify the situation. This is just 3D, right? And there's no speed. We don't talk about speed. So then this is just a wave function described in 3D. But things becomes more complicated if you include more and more particles. If you have n particles in the system, then you need to keep track of the position of each and every one of the particles. The description, just the mere description of the wave function, will need at least 3n variables. And this before talking about solving for the wave function itself. Because solving the wave function will involve you to solve a partial differential equation in 3n dimensions. Now, I can't draw 3n dimensions, so this is just an artist's impression. Okay. So then it seems as if the Schrodinger equation approach can't allow us to study systems with large particle numbers. Is there a way out of this? Fortunately for us, there is a way out. Otherwise, I won't be giving this talk. So in the year 1964, Pierre Hohenberg and Walter Kohn came up with this Hohenberg-Kohn theorem. What does this theorem says? It says that, and what they did is they used proof by contradiction, and they found that there's a bijective relationship between the ground state particle density and the ground state many-body wave function. Okay, what do I mean by proof by contradiction? It means that if this is not true, then the world explodes. And also, at this point, right, often I will get this particular question. What is a particle density? Yeah. So in a very simplified description, particle density is really just the number of particles distributed over a volume. So for example, if you distribute it over a line, 1D, right, then you just distribute it over a line, right? If you integrate over a particular region, then it gives you the number of particles that you expect to have within that particular region. Naturally, if you integrate over the whole line, then you get the total number of particles you have. So particle density is really just number over the particular volume they're looking at. Now, how does the particle density relate to the many-body wave function? Well, this particular equation. And you can see that you're integrating over all of the position but one, right? So this is how particle density is related to the many-body wave function. And already here, right, you juxtapose this particular expression to the Hohenberg-Kohn theorem, and you see something weird, right? The theorem says that the ground state particle density is equivalent to having your ground state many-body wave function. But if you just look at the math, you see that you integrate out a lot of information. How do you have the same amount of information in something that has less variables, right? The more particle you have, the more variables you need to use to describe the many-body wave function. So 3n variables. But the particle density, regardless of the number of particles, you always have 3, right? 3 position. In a nutshell, what this theorem tells us is that the many-body wave function is actually just like a self-help book, right? You guys have read self-help book before, right? A nice 300-page tome. You read through it. The stories are nice. It helps you apply. But to be honest, all you really need is just the table of contents. So this is exactly that. The particle density has exactly all the information that you need to get all the properties that you want. So corollary would be that any properties that you want to represent or want to study can be written as a function of your particle density. Now, so some of the mathematicians in you will just object me right away because I use the word function, right? A function is a mapping from a number to a number. But then now, a particle density is obviously a function. So the proper name for this particular function of the particle density should be functional. So hence the name density functional theory. So this is where density functional theory comes from in terms of the name. Okay, cool. So now I've established that, okay, as long as we have the ground state particle density, we can have everything. But there's a catch, right? Where do I get the ground state particle density to begin with? So, as the name suggests, ground state, right? Ground state means the lowest energy. So naturally assumes, it suggests the approach that we look at variational principle, right? We find an energy as a function of particle density, minimize over the density, then we find the ground state energy and the ground state particle density. In fact, the existence of this particular energy, as a function of the particle density can be proven rather easily. And this is based on what Nell Levy and Elliott Lee did during the 1970s and 1980s. And the argument goes like this. So I'm sure you have learned the usual variational principle before, where the ground state energy is just minimizing over all possible many body wave functions. Suppose we have a space like this. These are the different states, and this x is the minimum. Okay, so variational principle. If you just go through everything, you find the minimum eventually. But we can always do this minimization in two steps. First, we categorize regions in which it gives a particular particle density, right? So we do a minimization over a fixed particle density, and then we minimize over all the particle density. You're just splitting your minimization into two steps, and you still get the same result anyway. Okay. Then if you look at the expression, this particular step, where you have a constraint search, is what we define for the energy as a function of the particle density. Okay, so this proves the existence of En. So cool, now we have En. We just need to do functional derivative, set it to 0, and that's it. We find the minimum. And again, often at this point, I also get questions like, oh, functional derivative, so difficult, I'm out, right? They just tune it off. But I'm here to tell you that you actually learned this before. So let me have a quick question, right? Who here have not heard of Lagrangians before? You see, everyone heard of Lagrangians, right? So if you heard of Lagrangians before, you remember that you have your action principle of stationary action, yeah? Your action is your integral of your Lagrangian, and then you get your Euler-Lagrange equation. The Euler-Lagrange equation, this, is really just a functional derivative of your action with respect to the path. So you did learn functional derivative before, so you don't have to be afraid of it. The idea is just sort of like basic calculus. You do a first order derivative, set it to 0, and you get your minimum. Okay, so there it is, basic idea of density functional theory. You find the energy as a functional of the particle density. You use variational principle, you get your ground state particle density, you get your ground state energy, and you get everything. So that's the basic idea of EFT. That's the end of my presentation. Thank you very much. Oh, wait, sorry. I forgot one part. All the theorem that I said before, they are exact, okay? None of it, there's no approximation needed, right? When you really get the ground state density, you really get everything, right? So the whole formalism is exact because, yeah, that's the end. Some of you are like just smiling snidely because you know something is fishy, yeah? So what's fishy about this, right? Let's think about it. So the basic premise of DFT is this. Find the energy as a function of the particle density, apply a variational principle, you get your ground state density, and you have everything. The fishy part is, okay, how do I get En in the first place? That's why I emphasized earlier on about proof by contradiction, right? The proof is a proof by contradiction. All it proves is that this thing exists, but it never tells you how to construct it. Even the seemingly constructive proof that I showed you earlier, this Levy-Leib constraint search, it's not practical. You can't really just minimize over your many body wave function with a fixed particle density. So all these are just existence proof. But because we don't know exactly how En looks like, we need approximation method. This is only then when the approximation method comes in, right? Because the formalism itself is always exact. Okay, so how do we begin to approximate En, right? Usually we split the En into three different terms. There's kinetic energy, potential energy, and interaction energy. And lucky for us, right, the potential energy has a known form. Okay, so it looks like this. Fine. So all we need to do is to find an approximation for kinetic energy and interaction energy. So let's do this by steps, right? Let's first focus on kinetic energy. How should we begin to approximate the kinetic energy? Now, so the simplest approximation that we can have is by Llewellyn Thomas and Enrico Fermi, called the Thomas-Fermi approximation. Okay, and then it gives us that the kinetic energy has the particular form, where Nr, again, particle density, D is the dimension of the system, so it can be 1D, 2D, or 3D, and CD is just a particular constant for this. I'm going to hide it because it has different constants for different dimensions. Okay. Can any one of you guess when this is discovered, considering that DFT is discovered in 1964? So the funny thing is, this is discovered in 1927, almost 40 years before DFT is found, right? So this is also something that excites me a lot, right? DFT already had a model before DFT is found. They were doing DFT before DFT is cool. So it's good. Always makes me very, very excited that this happened historically. But yeah, so this is the simplest that we have. It has been there since 1920s. Is there a better way to, oh, sorry. Before that, let me show you how it performs, right? So the Thomas-Fermi approximation has very crude approximations or crude assumptions on the model. And yet, it kind of behaves kind of okay. So here are two examples in harmonic oscillator and a Mozart potential. You see that the density sort of captures the exact without the wiggles in the between. And also it has this artifact where it just goes to zero immediately. So as the number of particles increase, we will see that Thomas-Fermi will agree better with the exact solution. But then, of course, most of the time when we calculate stuff, it's still not accurate enough. Is there a better way to do this, right? Of course, we can go by the direction of what von Weizsäcker did in 1935 by adding more correction terms, right? So instead of just the particle density, we add in the gradient of the particle density to add correction terms. But that's not the best that we can do. The best that we can do is actually proposed by Walter Korn and Liu Zhushang in the year 1965. What they discovered is that we have the particle density, right? So that's still our base variable. But what's stopping us from parametrizing it differently? What they did is like, okay, let me just use some helper wave functions, or called auxiliary single particle wave functions, and parameterize my particle density like that. Sometimes this particular term is also called orbitals, right? Okay, if I rewrite or parameterize my particle density in this form, then I know how my kinetic energy should look like. Just the usual kinetic energy term wedged by the single particle wave function. Okay, so I often get this question as well. So to talk about that, first I have to get everyone on the same page. What is Hartree-Fock approximation? So Hartree-Fock approximation starts like this. You have your many-body wave function, and of course, you want to use variational principle. In variational principle, we usually come up with an ansatz when we minimize over the parameters there, right, to find the best fit. So here you can think of it as, okay, I just think of it as a product of different single particle wave function. But this is not right? Because if you do exchange of two particles, then you don't have the antisymmetric property that we expect from fermions. So then Hartree-Fock is like one step further. Let's build a determinant here so that we have the antisymmetric property. And then after that, I minimize over all wave functions of this form. So by definition, this is an approximation method, right? Your Hamiltonian is still intact, and you minimize over wave function of this form. This is Hartree-Fock approximation. Of course, you get some other expressions, but I'm going to hide it for now. But DFT is different, right? DFT, these things are just parameterizations. These are not supposed to be physical, right? Eventually, so because this is just a parameterization, DFT, this constraint DFT is still exact in theory, which I'll come to that later. But the difference is that this are not physical. This is an approximation. So this is the main difference between the two. They are not the same thing, even though their equations may seem similar. So you use variational principle on this particular parametrization and you get a set of equations, right? This formalism is called, like I mentioned just now, the Kohn-Sham DFT, named after Kohn and Sham. So you have a set of equations, they all depend on each other. How do you solve them, right? So you solve them by using the self-consistent method, right? So generally, this is how it goes. You guess a particle density, then you have to update your potential, plug it in here, solve for psi, update your particle density. Then you repeat until you converge. Converge means that the difference between your guess and the updated particle density, are they close to each other? Are they not? If they are close together with certain parameters, then yeah, you get your solution. Okay, so this is Kohn-Sham DFT. It's the most accurate version of DFT that we have right now, and it's exact. And here's when I answer your question, right? So why is it exact? Because surely the real kinetic energy looks different from the non-interacting version of the orbitals, right? Okay, so the trick here is that we parameterize the particle density in that particular form. What we are doing is we are mapping an interacting system to a non-interacting system exactly, right? So yes, the kinetic energy looks different, but we are hiding all those extra terms into the interaction. That's how actually it's done. There's a definition of exchange correlation energy, which comes later as well. And you see that those terms are hidden inside that thing. Okay, so here we are, right? So with the right choice of the interaction energy, we'll get the exact theory. And this is where things get a bit complicated. Because when we come to interaction energy, there's a whole zoo of different functionals that you can choose. And this is also the part where I get a lot of questions most of the time. Before that, let's just put something right. So I mentioned just now exchange correlation energy. So this is defined by, so historically, this is applied to electrons. So they actually sort of filter out the term in which you have your Coulomb interaction. Whatever remaining is called exchange correlation. And then it's this exchange correlation that has a huge zoo of different functionals that you can choose from, depending on the system that you're studying, right? And not just that, right? So sometimes you can even pick like two of the different things and merge them together into one particular function that you use. If you don't believe me, right, there's actually this particular website that I want to show. Cypher. Cypher is a program which allows you to do DFT calculation. And here is a web page of a list of exchange correlation functional that you can find in this particular program. So I'm just going to slowly scroll down. So I think I made my point clear that there are many different functionals. I'm not going to be able to cover every single one of them. But what I'm going to do is going to give you a rough idea of how to go about choosing the exchange correlation. Is DFT just mean field theory? So in mean field theory, what we do is that we have a system with a lot of particles, right? Of a lot of particles. What we do is in this approximation, we just assume that there's just one particle, and the effects of all the particles is just averaged out into a particular field. Okay. So whether DFT is just a mean field theory depends on how you view the term mean field theory. So the answer can be yes or no. If what you're saying is that mean field theory means that, oh, I have effectively non-interacting system, then yeah, you can call it kind of a mean field theory. But you have to understand that the mapping between interacting and non-interacting is exact, right? It's not an approximation per se. I mean, until we made an approximation. But the original idea is that you can also have other exchange correlation built into the formalism, right? So it's not just like a fully non-interacting system. So if your understanding is that it's an approximation where you can't add in any exchange correlation inside the system, then the answer will be no. So in a kind of weird way of describing this, I would say that, oh, DFT is kind of like an exact mean field theory, if you will. So how do we go about choosing the XC functional? Yeah. So I'm not going to tell you all the functionals. I'm just going to give you the rough idea of categories. So what we have. So there are two main categories. There's the empirical one and the first principle one. Empirical, as the name suggests, you do experiments, you measure some stuff, you get a particular model, then that's your function. First principle, what you do is you sit down, pen and paper, you calculate what are the constraints, what are properties that you're supposed to expect from this exchange correlation functional, you propose a model from there. So these are two basic ways to get your model. But again, this is just how you get a model, right? But what the model includes, that's a different category. And for that, I would have to use what John Purdue did by saying Jacob's ladder, right? So he called this the Jacob's ladder, depending on what information you put into the particular model. So at the lowest rank, right, would be the local density approximation, in which all you have in the model is depending on just the particle density. One level up, of course, like before, you see the von Weizsäcker correction where you have gradients, then this would be the generalized gradient approximation. And I think at this point, you can sort of think that, okay, the next rung, of course, is going to be Laplacian, right? Second order derivative. But also because the Laplacian is related to the kinetic energy. So sometimes they also include the kinetic energy density as part of the ingredients for the model. And at the last rung, of course, you put in exact exchange term into your functional, and then you mix it with whatever that's below. So these are the basic categories of exchange correlation functionals that you can choose from, probably. So as you go from bottom to high, you increase in the number of physical information you put into the model. Then the natural assumption is, of course, if I go from lower to higher, then it's more accurate, right? Because I'm putting more physics. The answer is no, because it depends on how the model is built, what particular constraints it chooses. So at the bare minimum, we have to accept a particular fact that there's no universal best functional to use, right? Different functionals will have different assumptions. What you have to do is to look at literature, identify what particular type of interaction you are interested in. Is it a system with strong correlation? Is it a system with low correlations, particular interactions that you're looking at? And then look for suitable functionals to use. If you found an empirical model that is chemically close to what you're doing, then yeah, using that may work better because it's the exact value, yeah? Otherwise, we usually try to go for first principle approximation because it's the more general one. Finally, because I always also get questions like this, can you just give me some example? So here's a cheat sheet of popular choices of XC functional. So generally, for material science, when you have extended wave functions, you use PDE, which is like a GGA approximation. For chemistry, when your wave function is more localized, then you go for B3 lim. And this is a type of hybrid GGA. Okay, so here we are. We have the energy functional. We pick the kinetic energy. Oh, sorry. We use Concham to solve for the kinetic energy. We know how the potential energy looks like exactly. And we also choose a particular XC functional. What we get in the end is the ground state particle density and the ground state energy. Okay? And then we say that, oh, we can get everything. But what do you mean by everything, right? So what properties can we get from just the ground state energy and the ground state particle density? Turns out a lot, right? So for example, so I'm just going to give you examples because just this year there are 10,000 papers. I'm not going to give you everything. So for example, here, right, you can get about geometry, right? Like I said, in equilibrium, you go to minimal energy. So you can actually calculate the energy, like for example, bond length, yeah? Vary it and find where the minimum is, and that's your prediction for the bond length. The same goes for bond angle, same things, right? But of course, if I just vary around the minima, right, then I also get vibrational modes of the system. The same goes for crystal structures. I can calculate the energy for different crystal structures, find which one is the. Again, you fix a particular crystal structure, you solve for the energy, the ground state energy that you can get for this structure. And then among all this energy, you find the minimum one, and that will be your prediction of how this crystal will look like as a structure. Okay. Then of course, you can also do something like, suppose I have n particles in the system, calculate the energy. I take one particle out, then you get sort of an ionization energy. Or the density itself, right? Suppose you have a particle density distribution of two different spins, then you can actually get the polarization of the system. And like I said, there are 10,000 different papers already this year. I can't go through all the particular applications, all the things that you can calculate just from this. but I am going to highlight my personal favorite. So these are my personal favorites. Like, so you can use DFT to actually design catalysts to increase to design your catalyst so that you increase the reaction rate. You can also use DFT to study situations in which you can't reach in experiments. Like, for example, core of Jupiter, high pressure situations you can't reach in experiments, but you can try to understand it using DFT simulations and calculations. Or you can use DFT to try to help you design biomolecules for applications that you want. So all in all, there are a lot of applications in DFT that I can't just go through. But there are different versions of DFT. I only presented the most basic one. DFT is like an EV, if you know Pokemon. You have different evolutions. So here are some examples on how you can evolve into different ways. So what you asked earlier, you have a finite temperature version where you put in statistical mechanics to, instead of minimizing the energy, you minimize over free energy and so on and so forth. You can also do dynamic stuff with time-dependent DFT. You can talk about excited states if you modify your formalism a bit. You can include magnetic field into your system, and then you have to add in current density into your formalism. Or instead of just the particle density, you can use your density matrix to form your functional theory, because the particle density is just the diagonal of your density matrix, right? So all of these are current research directions. You need more, I need way more time to describe each and every one of this. But just to give you an idea that there are still a lot more things to be done for DFT, different versions, fun. And now I'm going to address two common questions I also have about extensions of DFT, right? So first question I usually get, like, can we use machine learning to do DFT? The answer is yes. There are actually efforts in trying to use machine learning to learn what the functional is, because we know it exists, we just don't know what it is. So maybe a machine learning can help us find what it is exactly. So here, in a paper in 2022, DeepMind is trying to find some. So exciting. I'm waiting to see what they're going to get eventually. Second question, right, is can we use quantum algorithms to do DFT? The answer is yes, and there are papers that are trying to. This two paper is sort of like a hybrid between classical and quantum computers to try to solve DFT. But so if you're interested, you can go to these papers and then you read about it. This is what I'm going to talk about, the basics of DFT. Of course, I skip a lot of details because I don't have enough time. But I hope this gives you the basic idea of DFT, right? So the basic idea of DFT is just this. So we start off with Hohenberg-Kohn theorem, which says that all we need is just the ground state particle density. Once we have the particle density, by this theorem, we can express any properties we want theoretically as a functional of the particle density. In particular, the energy can be written as a functional of particle density. And using variational principle, we can get the ground state particle density and the ground state energy. And all this, the whole formalism is exact. The problem is, even though we know En exists, we don't know what it is. That's why we need approximation methods. Some of the simplest approximation would be the Thomas Fermi approximation, or you can add some gradient correction. But the most accurate version that we have is something called the conjunct DFT. And this is an exact formalism. Formalism is exact doesn't mean the whole thing is exact. The problem is because we don't know what the XC functional is, right? So when you choose an XC functional, it becomes an approximation method. And after that, you plug it in, you solve the variational principle, and in the end, you do application. So this is just the basic idea of DFT. It's not really that difficult. Yeah. So with that, I'm going to end. But before I end, right? So a few words from the sponsor. Okay. This presentation is sponsored by me. So yeah, I think part of the point of this presentation is also to tell you what I'm working on, right? So what do I do for my research particularly? So my research is on developing methods for DFT, and we view methods, quantum many-body methods in this particular picture, right? So usually in an ideal world, we want something that's scalable, transferable, and accuracy. Scalable means that we can go to whatever particle number we want. Transferable means that it's general, that it can apply to many different situations. Accuracy means, well, accurate. So for example, the Schrödinger equation will be a very accurate and transferable method, but it's not scalable because as the number of particles increase, it becomes very difficult to solve. On the other end of the spectrum, Thomas Fermi approximation, very scalable, transferable, but it's not very accurate. The best method we had just seen is the Constant DFT, which is reasonable scalability, quite accurate, quite transferable. The problem is, if you want to go to higher particle number, then it's a bit difficult because at the end of the day, we're still solving a single particle Schrodinger equation. So my research is sort of, I don't want to use this. I don't want to use orbitals to help me. In a sort of orbital-free DFT. Sure, I may sacrifice some accuracy, but at least I can study situations in which we can't study in conjunct DFT, right? By having more particle numbers. So in particular, for my research, I focus on this particular, another variant of DFT called the density potential functional theory. Not going into details, just going to give you a glimpse of what I'm doing. Here we have this variation in which the effective potential becomes the variational variable. You do the variational principle and you get a set of equations. And this should remind you of the quantum DFT earlier, because effectively, physically they're different, but effectively, you can see that, I'm just replacing the quantum particle density with this particular new form. So that should remind you that, then that means this is an exact formalism again, provided that I have exact interaction and I know this exact. But, life is not kind. You don't know these exactly. So then again, you need approximation method. So in this 2018 paper, there are a few approximations that I was involved in the paper, and then we have some approximations that we developed, right? And this is how it looks like. And my current research in Queck's group is to apply this method onto different situations, particularly atomtronics. Now, what is atomtronics? Atomtronics is electronics, but use atoms instead. So ultra-cooled atoms as electronics, you build circuits using matter waves. So here's a preliminary result. I'm writing the paper now, so I'm not going to say too much before I publish it. But you see that here I have two component fermions, so spin up, spin down. Think of it as spin up electrons, spin down electrons in a particular trap. And as you increase the repulsion interaction, you can see that they are separated. And they have, so effectively what you did is you implement a filter component for atomtronics. And I can calculate this using this method up to like 10,000 particles, which is difficult for quantum DFT to do. Another application which I'm not involved in, but I think it's fun enough to share, is by one of us, Martin. Martin is not here today, but he applied DPFT methods onto ecology. So if you're interested, you can ask him for it. I think he'll be glad to talk about it, but it's awesome. You use the DPFT methods to calculate fly distribution and evolution and stuff like that. That's fun. Okay, so that is one part of my research. Another part of my research is, if you remember just now when we were talking about everything, we only focus on the position space. But if you recall the minimization procedure that I said just now, why does it have to be position space? It can also be applied to momentum space. So I'm also trying to develop a momentum space version of DPFT. Now, why do I want to do it in momentum space? Well, it's because momentum density is something that you can actually measure in experiment. It'd be nice to have a self-consistent theory to have like a momentum space density. Of course, when you shift things into momentum space, things look differently. The approximations will be different. So it wouldn't replace position space per se, but it will complement what we have in the position space version of DFT. So here's a preliminary result. This is very far away from publication yet, but this is like the first result we have. Suppose you have two spin components in a harmonic trap interacting with a contact interaction. You see that the momentum density looks like this, nicely symmetric. But if you compare it with the position space, right, you wouldn't guess this particular form. Because my first intuition is like, you have something like this, it assumes that it's rotating, yeah? But if it's rotating, then why do you rotate at different speed? Right, you have different density profile for different components. I don't have an answer yet. This is like really, really preliminary result. Hopefully someday I would have an answer for this. But at least, yeah, this is what I'm doing. Now, we can take a step further in terms of DFT in different spaces, right? Why just position and momentum? Now, suppose I do DFT in the single particle Hamiltonian space, right? So the eigenstate would this, yeah, and then we would have number of particles in this particular state that function as the particle density, right? Why don't we do that? We did that in this particular paper, and we called it a single particle exact DFT. Yeah. So the result is that now, why do we want to do it like this? It's because before in the position space DFT, we know that Dr is exact, but the kinetic energy we need to approximate. Here, by using the eigenstate of the single particle part, this whole thing is exact. I no longer have to worry about kinetic and position, and the potential energy. All I have to focus on is to find the interaction energy. And of course, if you're interested, you can look at the paper. There are results that we have. This is one example. But I know I'm rushing at the end of this, but I'm just going to give. I was just planning to give you a glimpse of what I'm working on, what kind of things that I'm developing in terms of DFT methods. If you're interested, you can always come and find me and discuss about this. Maybe when I'm better. But that's sort of the main point, right? So with that, I thank you for your attention and thank you very much.